Hello everyone, welcome to the 8085 microprocessor practical series. So this is the next practical number 6B. Okay, we have written 6A. Now in this particular practical, this is what we have to do: calculate the sum of series of even numbers from the list of numbers. The length of the list is in memory location 2200H, and the series itself begins from memory location 2201. And assume the sum to be 8-bit number, so you can ignore carries and store the sum at memory location 2300H. So in this particular case, what we are given is that we have some data in the memory location, so it begins from 2200. At 2200 we have the count. Like suppose if you want to add 7 numbers, so here we will have 7. Okay, so whatever numbers we have to add, they are at this location. Okay, and immediately after this the numbers will begin. Okay, so here the first number will be here at 2200 to the next number will be here. So we have to add all these 7 numbers starting from 2201 in this particular case, and after addition the sum should be stored at location 2300. So the sum should come here, and we have to take care that only even numbers should be added. Okay, so even numbers, of course, which are multiple of 2, or which can be divided by 2 actually. So all the numbers which are divisible by 2, they are even numbers, so only even numbers in the series should be added. Okay, so we have to do that. So this is the particular program. Now in case of 8085, how do we know which number is odd, which number is even? So let me give an example. Like suppose in case of 8085 we use hexadecimal notation. So the one of the number starts from 0, 1, 2, 3, 4. It goes up to numbers, then up to 9. Then after 9 we have A, B, C up to F. Okay, now any number which we are having in case of 8085 is a hexadecimal number which has only this number of digits. Now 0 is actually 0000 in binary, 1 is 0001, 2 is 0010, 3 is 0011, 4 is 0100, and so on, and A is 1010 and B is 1011. Similarly the F is 1111. Now it is seen that all the even numbers, they have this 0 on the least significant bit is 0, and for odd numbers the least significant bit is 1. So we only, whatever be the number, we only check the least significant bit. Okay, like suppose we have any number. Now in this case we have only 8-bit number, so 8-bit number can be like, let us take 13, maybe 4F, 39, 46, and so on. So this 13, if we write it in binary, it is the code for 1 is 0001 and 3 is 0011, and 4F, so 4 is 0100 and F is 1111, and 39 is 0011 and 9 is 1001, and so on. So in this case, let me write this 4 is also, so this 0100 and 6 is 0110. Now this bit of the number is 1, so it is odd number. This bit is 1, it is odd number. This bit is 1, it is odd number. This bit is 0, so this is even number. So we only need to check the least significant bit of the number. If least significant bit is 1, then it is a odd number. If it is 0, it is a even number. Now how to check in case of microprocessor 8085? So what we'll do, we will transfer the number from memory location to register A, and after transferring to register A, we use the instruction rotate right. There are two rotate right instructions. One is RAR, okay, and one is rotate accumulator right through carry. So this RRC. So this is rotate accumulator right through carry, and this is simple rotate accumulator right. In both the cases, of course, the least significant bit will go into the carry. So if after using this instruction, any of the instruction, if carry is set, it means the number is odd. If the carry is reset, the number is even. So we'll use this particular principle. We'll use this RAR. So with RAR instruction, the data in register A will be rotated right. When it rotates right, the rightmost bit, that is this least significant bit, it goes into the carry. If carry is set, it means the number is odd, we need to ignore that number, we don't need to add that number. And if carry is not set, then we need to add that particular number. So this is the given program. So we start with the first instruction, Alexa H2200. So this instruction is actually used to point to the memory location. Now this, the very first memory location, it contains the count. Count means the number, the total numbers which we have to add. So suppose if 2200, if it contains 5, it means we have to add 5 numbers. Then we next instruction is MVID00. Now this instruction will initialize the data, the register D with 00. We have to add the partial result, so we have to actually clear this register D. Then next instruction, move C comma M. Now what this instruction will do, it will load this count into register C. So C contains the number, the count which we have to add. Then INXH, what INXH will do, it will point to the next memory location 2201, which contains the very first number. So we take the first number from memory location to A. RAR as we know, it rotates the contents of register A right through carry. So this will ensure, this will tell us whether the number is even or odd. Okay, now RAR, if carry is generated. Now if carry is generated means the number is odd, and we skip that number. So here we have JC 8005, so it directly skips to this part, that is it decrements the count. Okay, so now count was 5, now it becomes 4. Now here the next instruction, JNZ. Okay, JNZ will check whether the count is 0 or not. If it is not 0, it goes to the next number, so it is JNZ 8006, so it comes to 8006. Here is 80, it increments the memory pointer, takes the number into A. Okay, take that number into A, and RAR. Now suppose if carry is not generated, as in this case, if carry is not generated, then what will happen, that number has to be added. So it will skip this part because the carry is not generated, so it won't go to 800F, but it goes to immediately to the next instruction. So here we again have this move M comma A. Now why this M comma A again? The numbers was already there in A, but because we have used this instruction RAR, so it actually changes the contents. Whenever the data is in A and we rotate the content, it actually changes the contents. Okay, so we have to again get the original number again, so we use this instruction and add with D. So add with D, so because we have to store the partial result in D, but D was already 0, so A plus D equal to A, so the result is now in A. Okay, now move D comma A will ensure that the whatever the result we are having, because we are not done with all the numbers, so we need to store the partial result in register D, so we move the data to D. Then again decrement count, so this will continue. Now suppose all the numbers are added. Now when after all the numbers have been added, this J and Z will fail, it will come out of the loop, and because the result, okay, is in D, so this D goes into A. Okay, and with STA the final result gets stored in 2300. So this is how this program works. That is executed on the simulator. Now this is we have entered the code. Okay, now let us store some data. We need to store some data in the memory location, so that is we start with 2200. Okay, let us assume we have to add actually 5 numbers. We can add any number and any count, so I want to add 5 numbers which are even numbers. Okay, in there are the numbers are 5, but only I have to add those numbers which are even. So I start with let us start with odd number. I will just write 21 here. I will just add 10. Okay, and the next memory location here I'll just put 20, 23. Okay, and in the next location I will add 20. Okay, and here maybe like let us take 99. Okay, so these are the 5 numbers 1 2 3 4 5, so 2 1 1 0 2 3 2 0 and 0 9. Now out of these 5 numbers 1 0 and 2 0, they are only even, so what the result we get is 2 0 plus 1 0, so we must get 3 0. Okay, this is what the result we will get. So let us execute it. I'll just execute stepwise so that we can know what happens at each and every step. So the first step, LXI H2200, we get 2200 in H and L, and they also act as a memory pointer. And with the next instruction MVID, D00 gets stored in register D. With the next instruction, the count, the 05, it gets loaded in register C. Okay, then with INXH, the memory pointer gets incremented, we get 2201. In the memory pointer points to 2201. With move A, M, the first number which is 21 at location 2201, it gets loaded in register 2. And with the next instruction, we use RAR, so the data gets rotated right through carry, and we see the carry is set. It means that number is odd. We don't need to add the odd numbers. We need to skip that. So this JC, okay, JC will check whether the carry is generated. As we know, carry is generated, so it will skip this number and directly come to DCRC. It has skipped this part, addition part. So DCRC ensures that the first number is done, and we need to decrement the count, and if count is not 0, it will go to the next number. Okay, so it goes to the INXH. With INXH, we have the next number is 10. Okay, the next number is actually 10, which gets stored in register. With move A, M, the next number is 10, it gets stored in register A. Okay, so 10 gets stored in register A. Now this 10 was of previous data which was rotated. Okay, don't get confused with this. So now next number is 10. Okay, now with RAR we see carry is not generated because 10 is an even number. Okay, and because it is even, see after rotation with the number gets changed. It was 10, now after rotation it is 88. Okay, so therefore this step move A, M, it ensures that we get the original number again. And with add D was already 0, so A plus D, so 10 plus 0 is 10 plus 0 is 10, so we get the result 10 in register A. Okay, so we need to store that partial result in register, so this 10 which was in A gets stored in register D. Okay, then again we decrement the count, jump if no 0. Okay, it again comes to the next count. Now next number gets, so next number is 23, it gets loaded in register A. Okay, and with RAR, carry gets generated. As you can see, carry is generated, so the number is odd, we skip, the number gets skipped. DCRC, the count gets decremented, jump if no 0, we come to the next number. Now next number is 20. Okay, so this 20 gets into register A, and with this, because after rotation carry is not generated, it means the number is even. Okay, so the number gets stored. Okay, the number gets added. Okay, so we get the final result is 30. Okay, and this continues. Okay, I'll just run the program to end. Okay, the program has ended. So as we can see, the final result 30 is is stored in 30, and with STA the result gets stored in 230. So this is the result. This is how we get this. Okay, so this is how the program gets executed. So that's all for this particular session. You can execute this on any simulator, you'll get the proper answer. So that's all for this particular session. Thanks for watching.